Hello everyone, my name is Rohit Pillai and I'm really excited to present my research which I've conducted under the guidance of Su Wei Ho. The topic of my research is to build a predictive model on signal attenuation of a hybrid communication system which occur due to weather conditions. Before we dive in, here's a quick roadmap on what I'll be covering today. Background. In this section, I'll start by explaining a little bit about radio frequency system, free space optics system, a hybrid communication model, and most importantly, signal loss, power loss, which is signal attenuation. In the data subsection, we'll explore how the data was collected and what are its key properties. In the ML model section, we'll look at different modeling approaches and the ML model used to predict signal attenuation. Background. Here we'll be talking about the radio frequency and free space optic channel, hybrid systems, and the main objectives of the project. Radio frequency communication system is one of the most widely used methods for data transmission in the world. It operates effectively because it does not require any line of sight. It is operated by a radio transmitter transmitting radio frequency signals and a radio receiver receiving the particular signal based on the bandwidth. This led to the emergence of free space optic communication systems. To overcome the limitations of radio frequency, FSO was developed. It uses a laser beam for high-speed data transmission, and unlike the radio frequency, it does require a clear line of sight. However, FSO offers its own benefits, which are a higher bandwidth and it is more secure. A key important point to note is that both the radio frequency and free space optic system are highly susceptible to atmospheric conditions. Here we will be using a hybrid optical E-band correlated channel model. As you can see, this is a hybrid system model with both radio frequency and FSO. They would be transmitting at these frequencies and receiving at these frequencies, whereas for FSO, it will be same of the frequency. The important thing to notice here is the TSS and RSS. The difference between the transmit signal strength and the receiving signal strength is the power loss. The main objective of our research project is to predict the signal attenuation of the hybrid communication channel. We'll be achieving this by following two methods in model building. First method is to develop independent models for both radio frequency and free space optics. And for method 2, we'll build a one conclusive model which would predict both RF and FSO attenuation. About the empirical data, how the data was collected, the basic description of data, and the most important feature, which is the sign-up code. To ensure accurate modeling, we have collected empirical data from this bidirectional communication system which we saw earlier, as it operates both radio frequency and free space of optics channels. The system was deployed in 6 cities across 5 different countries, and it captures real-world variations in weather conditions and atmospheric pressures on signal transmissions. The dataset obtained through the system is quite large. It has 91,379 observations spread across 25 different features. It also has 2 different columns of RF attenuation and FSO attenuation, which was recorded by the system at the location. And this would be the target variables in our predictive models. Here, the table represents what sign-up code is. So basically, sign-up code is the categorical representation of all the weather conditions which we'll be using in our model building. Here, 0 denominates clear weather, 3 shows dust storms, 4 shows fog, 5 drizzle, and so on. The table tries to capture effectively all the weather conditions by making it numerical and making it easy for regression-based prediction models to operate. When we further look into the dataset, we come to know that the dataset based on the sign-up code is quite skewed. For example, the number of observations for clear, that is sign-up code 0, is more than 50,000, and it is quite high as compared to other observations. When we have a look at 6, which is rain, it does have 50% of the clear weather observations. It is clearly evident that for the dust storms, which is 3, and Snow, which is 7. Moving on, we'll be talking about the machine learning models that are used in the research. First, we'll be using and talking about random forest models, and second, in the approach, we'll be talking about two methods that were used. We will be using random forest regression as the base building model for all our models because there are advantages of using random forest regressor. That is, it handles large data set, complex relationship, and it is robust against overfitting. In the method 1 of the approach, we'll have two main steps. First step is to build 7 specific random forest models for each RF and FSO attenuation. In the second step, we would be using one generic random forest model which is trained on all the data for each radio frequency and FSO attenuation channel. Now, in the specific model, when the data is divided into training set and testing set, for the training set, the data is further subsetted based on their sign-up code. So basically, for sign-up code 0, all the observations in the training dataset which have sign-up code 0 is subsetted to form a dataset 0. Similarly, for all the 7 sign-up codes, that is achieved. Then, a random forest model is trained with all the features to record RMSE and R-square. That means the random forest model 0, which is trained on the subset dataset 0, initially uses all the 25 features available in the dataset. The next step is to implement a recursive feature elimination algorithm. We know that all the 25 features are not important and can hinder the performance. Hence, we implement a recursive feature elimination algorithm to find the best features and then perform a model refinement. So model refinement is after the algorithm is completed, we'll be left with certain important features only. And then we'll use those important features to retrain a random forest model each. In this particular algorithm, which is recursive backward feature elimination, we'll initially start with all the features in the model. As you can see in the graph below, these are all the features for a particular sign-up code 0 and radio frequency channel. It has 466 observations. Initially, with sign-up code, with all the 25 features, the RMSE and R-square values are calculated. After calculating using the out-of-bag error of the feature of the random forest regressor, we take out the least important feature. For initial iteration, it is sign-up code. So after eliminating sign-up code, the model is again retrained on the remaining 24 features. After doing that, we obtain a certain RMSE value and R-square value. These are the data points. So this is the RMSE, this is the R-square, and this is the RMSE obtained after eliminating sign-up code. Then the wind speed minimum, the next feature, then again using out-of-bag, we get the least important feature, which is wind speed minimum. Then after removing that particular feature, the model is again trained on another 23 features and RMSE and R-square values are calculated. After doing this, there comes a point where after removing a certain feature, the model, the RMSE jumps very quick and the R-square error drops very steeply. Hence, that cutoff point is determined and we draw a line. So any features on the right side of the particular line are all the important features, and all the features on the left hand side are not too important features. Similarly, the second step of method 1 is creating the generic model for RF and FSO. Here also, the algorithm of recursive elimination is done on the whole dataset. There is no specific dataset here, it's the whole dataset and one generic random forest of radio frequency and one random forest model for FSO is built. There a need for method 2 because method 1 seems sufficient, and I guess we have achieved the best results by tuning hyperparameters and getting the best features. Here, Why is there a need of using two separate models for both the target variables? And a very important question is that, is the collinearity between the RF attenuation and FSO attenuation preserved? In the method 2, we'll be using a joint model, that is, a single model to predict both the RF attenuation and FSO attenuation. So in this case, also to check if the collinearity is preserved, what we do is the first random forest model that we obtain from the method 1, the output RF attenuation predicted is taken as one of the features for the random forest 2. So when you're building the FSO attenuation model, all the important features that we got from method 1, that is we achieved through backward recursive elimination, we add one more feature of predicted RF attenuation to the random forest. Similarly, we can do the same for FSO attenuation. The model that we obtain from method 1, the output can be used as one of the features in a second random forest model to build a model and predict the radio frequency attenuation. We have not yet discussed on which model are we using. Are we using the specific random forest models or the generic random forest model for FSO? We'll come to it when we discuss on the evaluation part. The evaluation part. We'll talk about two things, the metrics and the performance evaluation. Here are the two important metrics that will be used for our evaluation. First is the RMSE, which is the root mean square error. It is basically the difference of squares between the actual observed value and the predicted value. And the mean is taken by endpoints to finally conclude the RMSE. The RMSE is the correct measure when you are trying to evaluate your random forest or a regression model in a regression model. As this is the Pearson correlation coefficient that was used to determine the correlation between the two variables. As you can see, x is one of the variable and y is one of the variable. Using this formula, you will be able to determine if there is a positive or negative correlation between the variables. Moving on, now we know that a lower RMSE score means a better model. Now, to evaluate the performance of specific random forest model and generic random forest model that we obtained from method 1. Here, the blue line represents the specific random forest model for RF and the green for generic RF. As you can clearly see, the generic random forest model clearly outperforms the specific model in case of radio frequency across all the weather conditions. And when we look at the FSO random forest models, here the generic FSO model, which is red, outperforms the specific model in few cases, which is the dust storm, the fog, and the rain. Also, as you can see, the RF models are significantly better than the FSO models. Only in a place of drizzle, the specific FSO model seems to do better than the specific random forest model. Hence, in conclusion, we know that the generic model is better than the specific model for both the RF and FSO. Now, as we know that the generic random forest models are better than the specific models, we'll use the output from the generic random forest model as an input for our method 2. So in method 2, we were using the output from the method 1 as an input feature to train another random forest model to output a certain target variable that we wanted. For example, now that we know that the generic random forest model for radio frequency outperforms all the models, we'll use the output from that model, that is the predicted RF attenuation, as an input feature for the FSO random forest model. Moving on to the conclusion findings. Here, our goal was to predict the signal attenuation for a hybrid communication channel. So, moving on to the method 2, that was building the joint models. Now we know that the output from the generic retiforest model for RF and FSO was better. Now, that was used to the predicted attenuation was used for FSO. Thank you all for listening.